All right, so on the screen, you can perhaps see, I hope you can see, a little website. This is a very simple user interface implemented in Scala. It's actually the old version, 80 says the wrong. Let's go there. And this is a to-do application. So we can do things like we can click on these little drop downs. This is the drop down, change shape. We get a extended description, and we can enter a new task we want, deliver a talk on finite state machines. Project, I guess, is Scala Lab, and maybe I can put some tags in here. FSM, finite state machine. I probably don't need Scala Lab as a tag because that's part of the project and so on. So that's one little example application I have here. And I want to show you a few other things. Here I have a little animation. Again, of course, the code is written in Scala to do this. And as you can see, the animation cycles between these shapes. We have circles, squares, and stars, and concentric versions of these shapes. And finally, here's a very simplified list of requirements of something that you may have worked on before, which is the login part of a web service. So you have things like when you create an account, you must send a verification email, and the user can't log in until they've verified their email address. Other things that perhaps an account is closed, user cannot log in anymore. Maybe you have things like an account can be locked for various reasons. Perhaps someone behaves badly or commits fraud or something like that, and user can't log in when the account is locked, but a lock can be removed, whereas a close is something that's more permanent. So just a very simple version of requirements that you probably interacted with either as a user of web services or perhaps an implementer of them. So the question is, what do they all have in common? And the answer, of course, given you my talk, is that they are finite state machines. And this perhaps raises a few other questions. So you might then say, okay, so what is a finite state machine? And why should you care? Well, I hope you do care a little bit since you're here. But the part of this talk, of course, is to explain to you the joys and benefits of finite state machines. So thanks for coming along to my talk, Finite State Machines for Functional Software Machinery. You're perhaps saying it rather late or getting it relatively early, so I appreciate that. And let's get into it. So the goals of this talk, we want to explore some of the different formalisms of finite state machines. So if you have studied finite state machines, you might have come across a whole zoo of different models and different terminology. So we want to discuss some of those, the formal aspects of it. More importantly, we want to focus on the use of finite state machines in solving practical problems and try to connect the theory to practice to show that finite state machines are extremely useful in practice. And what we know from theory gives us things that we can apply in practice. It's actually quite useful. So that's the real goal, demystify finite state machines and show that they're a useful tool for practical software development. All right, so what is a finite state machine then? Well, we can see a finite state machine is the following things. It's a finite set of states. It's an initial state, which is a member of this set of states, a finite set of inputs, and a transition function, which given a state and an input returns a new state. And then we might have a set of halting or final states, which are a subset of our states, and they tell us when the finite state machine has stopped. All right, so that's the definition of a finite state machine. We're good, we can go. All right, the end. Or not. Okay, so if you're already happy with that mathematical definition, then you probably studied these things before. But this is a talk where we're approaching things from the more practicing programmer's point of view. So we're going to simplify this definition and present it in a way that's more familiar to us programmers. So let's start just by simplifying. There are a few things here we don't really need. We don't need to define an initial state. That's something that can be provided by the programmer, say. And we're not always interested in finite state machines that halt. A lot of our finite state machines that we have in practice, we never really stop. So you think of those analytics types of things. There's no real endpoint here. They just keep on going indefinitely. So we can get rid of these two things. This is sometimes called a semi-automaton in the literature. The name is not particularly important, but I'm just putting it there so that we know if we read about semi-automation, this is what we're talking about. It's basically a finite state machine with some of the extraneous stuff removed. Set of states, set of inputs, and transition function. And now we can translate this into code. And what we get is a type of states. So a set of states becomes a type because a type defines a set of values. So that's a type of inputs, I, and then the transition function is just a function from S and I to S. And we could go ahead and implement this. In Scala, we might write something like this. A semi-automation is just, here I've used a type definite, type alias. So semi SI equals, and it's a function. There's a function SI to S. So that's our simplest version that we could start with. Now I want to make a quick note about the implementations here. I'm going to have implementations, but you shouldn't take them to be the canonical implementation. There's nothing that says that my implementation is better than other implementations. And there'd be various reasons you want to have different implementations. And that's something I'll discuss a little bit later. So these are just examples. This is not to be taken as like gospel truth. You don't have to implement a finite state machine in this way. You could do it in other ways. All right. So where do we use these types of functions? What are some examples of these finite state machines where we have inputs of two different types, then we return an output, which is one of those input types. So an AB to A, or as I had before, oops, SI to S function, same basic signature. One place where we would see this is in fold. So fold left, fold right have functions of this type. So say we wanted to add up the elements in a list. We have a list of integers, 1, 2, 3, 4, and 5, and we can fold on them. I've used fold right here because it just ties into something that's coming on later. The choice between fold right and fold left is not important. We could use fold left here. And we have an accumulating value. We have the current value we've seen in the list so far, and we add the current value to the accumulator to get the sum of the elements. All right. And this is the transition function of a finite state machine. Integer is a finite set of states. It's a type. All types are finite on computers because we have finite memory. So as our first example of finite state machine, so if you've ever written a fold, there's a very good chance you are actually using a finite state machine. You're probably using finite state machines a lot without necessarily realizing it. And this brings me to the core concept. We're trying to walk a balance between formalism, formalism is important for the theoretical computer scientist or the mathematician because they want to prove properties of finite state machines. You do things like proving equivalence of various transformations on them. But for us, the programmer, what we're really interested in are the conceptual concepts. And to me, the most important idea of a finite state machine is this. You have the state, which is some summary of everything you need to know about the history, what you've done so far. So it summarizes everything you need to know about what you've done so far so you can continue doing whatever it is you're doing. And then this transition function, which given the current summary and some input, you're going to use to produce the next summary. And that's the case in summing the elements of a list. Your accumulator, your sum so far, summarizes all the elements you've seen, adding them together. And then the transition function, given that accumulation and the current element, you produce the next accumulation by adding the elements together. And this idea of having basically sometimes called a step function, where you have an input and you want to go from this input to the next, adding the next little incremental bit of information into it. This is really the most important thing in my mind about finite state machines. And The reason for this is because it forces you to be really clear in your thinking. You need to say everything I need to know to do whatever I'm doing. And what's everything I need to know to do whatever I'm doing? And what do I do when I see an input of all the possible inputs? What do I do in all the possible summaries I could be looking at? In the case of adding up the elements of a list, it's really simple. You add them. But in a case where you have more complicated state and more complicated inputs, then you need to think about how they all interact. And that's what a finite state machine forces you to do. So this is the number one point that you should take from this talk. Finite state machine is all about thinking, what are all the different possible combinations of my summary of my history, my state, and the possible inputs, and what should I be doing in each case? And when you think of things explicitly as finite state machines, it forces you to think about that and make sure there are no cases that you've missed. All right, so a few connections that we talk about, how this connects to some other things that you may have heard of. We'll be peppering these throughout the talk, so there's more to come. Firstly, this idea of the Markov property. The Markov property, which is something which comes in more statistics than in computer science, but you may have heard of it, this idea of summarizing the history in some bit of information. That's our state. So if you hear of Markov chains or Markov decision process or something, they're all around the same idea, basically finite state machines. And the other thing that some of you may pick up on is you may think that folds are related to monoids. So if this function that we pass to a fold is the transition function of a finite state machine, is there some relationship between folds and monoids? And yes, there is. Finite state machines are monoids as well. And we'll be coming back to this point. All right. Another thing I want to talk about here is the reasoning principle for structural recursion is the same as the reasoning principle that we had for the transition function. And what I mean by that is this idea of saying, okay, I've got my summary of the history so far. I've got my current bit of information. What do I do to combine the summary with the current bit of information? So if we take the fold we looked at before and rewrite it as a recursion, we get this. So this is the fold we started with. We write it as a recursion over a list. And this is why I use fold right rather than fold left, because fold right is just a little bit simpler to write as a recursion. This bit here is the transition function that we saw earlier. And that's, again, the way you think about this is exactly how you think about the transition function of a finite state machine, the way you think about this recursion. So the naive way of thinking about recursion is to sort of try to expand the recursion, say what a sum do is recursive, and then sort of expand this out in your head, and you'll soon run out of stack space in your head and get a stack overflow. And that's not a very fun thing. So the way you think about this as a programmer is you say, okay, I'm assuming this is going to work correctly. It's going to give me the sum of the tail of the list. What do I do given the sum of the tail and the current element to produce the next bigger sum? Well, I add them together. And that's exactly the reasoning principle we used in the transition function of the finite state machine. We said, I have my state so far, my summary of the history, which is the summation. What do I do with the current element to produce the next summary? Add them together. So it's exactly the same reasoning principle we use in dealing with structural recursion as we deal with in the transition function of a finite state machine. So possibly an interesting connection there. Yeah, it's a little bit weird giving the talk without really being able to get feedback. If there are any questions or anything, if somebody wants to interrupt me, that would be absolutely fine. I can hear lots of notifications, but I got them turned off because they appear on my screen and they're kind of distracting. But if one of the hosts wants to send questions my way, that's fine. Otherwise, I'll keep on going. All right, so let's move on. Now, we've looked at some very simple examples of finite state machines. We saw summing on the list, and we've seen some of these things like here we had, this is a finite state machine I told you, but there's something special going on here in this finite state machine, and that's what we have output. So to add output to a finite state machine, we need to augment our model. And in any practical application, I won't say any practical application, most practical applications are going to have some output as well. So we need to add this to our model, and this is, again, connects to theory, where this is often known as a transducer. So a transducer is just a finite state machine where we add some output to. All right, if you've heard of this, you may have heard of Mealy and Moore machines, two main formalisms, and they're relatively straightforward. So this is the definition of a transducer, the Mealy machine edition. And everything here is what we saw before. And here we have an output function, which is saying, given the state and the input, I choose an output. Sorry, this is new as well. We have a set of outputs. And in the Moore machine, we just have a simpler output function that depends just on the state, not on the input. And when we have this model, we can start talking about some of the examples I showed earlier as finite state machines. So for example, in this animation, the state is what's displayed on the screen. Sorry, let me go back. The state is a summary of where we are in the cycle. So each shape grows 1, 2, 3, 4, 5 elements. And the input is just a clock tick. So it's just a regular, I think it's 200 milliseconds. We produce the next output. And the output, of course, is the shape that we draw based on this summary. So in this case, because the input is just a clock tick, it's not really important, we have a Moore machine where our output depends just on our state. So the state just being a summary of which shape are we showing and how many concentric shapes are nested. If we go at this application, this to-do application, there's quite a lot of state here, and you can think of either as many finite state machines or one big finite state machine. So for example, here we have in these drop-downs, we have the expanded or collapsed state, and that will determine the information we display. Do we display this or not? And this rendering here of this drop-down, which way the arrow points. So that's an example of the state there in the state machine. So when we get a click, will be one of the inputs here. We change the state, expand and collapse, and we choose what we display based on that. Here we have quite a bit more state. Our state, we have a title, a description, a project, and possibly some tags. And there are many different inputs, such as deleting a tag, adding a tag, changing some of the fields in here. So that's a more complicated finite state machine. And the output is what you're seeing on the screen. Okay. So back to the slides. So these transducers are the most practical type of finite state machine, the type that I usually work with, and I expect the type you'll be working with most of the time. And we can implement them, say, as follows. We say we have a function which is from the state and the input, and we return a state and an output. We can write this in a slightly different way if we like. So one thing that we can do is sort of wrap the output up as some kind of effect type and say, here we have an effectful finite state machine. So F could be like your IO type, for example, if you're into that kind of thing, if you want to model it that way as a more sort of FP approach. All right. So like I said earlier, there's no canonical implementation. It's down to whatever works in the circumstances you're working with. This is the type of thing you would typically have if you're, say, working with IO or future or something like that. And then you'd have, like in a web service context, for example. All right. So let's talk a little bit about examples. I talked earlier about some of these things. We can see them. Let's see something that's probably closer to what most people work on, should be a web service. Let's see how we can think of that as a transducer. So web service, unfortunately, need to scroll a little bit. We might have something like this. Our account service, which handles events that happen on a user's account. So we have some state. I call it state. We'd probably call it account in implementation, but I wanted to make the connection to the finite state machine clearer here. And then we have some event, and we're going to return an IO of an account. So the events could be, let's say, a user has verified the email, and we want to say if the account email is the same as the email address they verified, then we want to send them a message saying, well done, you've verified that email, we've taken a note of that, and you can now log into the account. Otherwise, we'll send a message saying, looks like your verification has gone wrong. Maybe you want to resend an email or something like that, and the account is not verified. So that's what we're doing on that input. And then we would have things like login, very common. So if the account is closed, then we tell them, sorry, you can't log in. If the password is not correct, we'd go, your username or password is incorrect, please try again, or get a password reset. Otherwise, we create a session for them, and then away we go. So these types of things that you possibly work on, possibly a more familiar example, and we see how we can present this as a finite state transducer. So we're transforming the account state and also having some other effect, which is sending messages back to the user, or sending messages back to maybe our front end on what to display to the user. And this gives us a finite state transducer. All right. Now let's talk about implementation techniques. So like I said earlier, there's no canonical implementation technique. I've shown some very simple ones previously. I do see two main classes of implementation techniques. So let's talk about those now. So one is called the reified case. So this is dealing with the inputs that we have to our transducer or finite state machine. And in the reified case, we represent them as data. So what we might have would be something like this. In the application here, we have, oops, I just dragged that, doesn't matter. We might have the state expanded or collapsed, and the action we here represent as a case object using Dotty's new syntax. And let's just put that back. Okay. And then our transition function is a function from the state and the action, which is the data to state. All right, so that's one way of doing it. Our actions or inputs are represented as data, which you normally use algebraic data types, enumerations, sealed traits of final case classes, depending on which version of Scala you're working with. Right, this is the most common style, I think. And one of the big benefits of it is that you can serialize these actions or inputs, put them in your message queue, save them to disk for durability and so on. So in the web service world, in the distributed systems world, this is very common. It's not the only implementation technique though. The other thing we can do, one of the other main techniques is it's called church encode them. And what we do here is we merge the inputs into the transition function by having a method for each different input or action. So in the case of the account service, what we typically see are things like you might have an account service trait in your web service, and you'll have methods such as verify the email, close the account, and so on. And what we are doing here, this way, these methods are the inputs to the finite state machine, or the actions, and we merge them into the transition function. So each method here is a part of the transition function. It says what we do given the state we're passing in here and the input, which is the rest of it. So we can think of each one of these as being part of the transition function, the entire collection of methods defines the complete transition function. So this is what you'd usually do if you had, say, a web service with a routing DSL. But at the end of the day, it's the same thing. It is a finite state machine. The advantage of this, well, it avoids some allocation because we don't have to allocate the data structures for the messages. That may be useful in very high performance systems. It's a little bit more idiomatic in the web service world just because most of them have these routing DSLs, which make it natural to write in this way. Look at the request, pull out the different parts of it, and figure out what method you want to call based on that. Okay, so the point here is different implementations, but same underlying idea. You can deal with the same mental model to think about this, and you can choose implementation depending on the properties you want. Okay. Another thing I want to note is that in the theoretical model, the state is not meaningful beyond what the state is itself. So there's no like structure inside the state. Again, this is something, it's not something we should get hung up on. Putting structure, putting data inside your state is absolutely fine. There's no theoretical computer science police who will hunt you down if you do this. And yeah, it just basically is a way of factoring the state to make it more manageable. Okay. Right. Now, so I've talked about basics of finite state machines, how we can implement them, some of the examples of use, but I want to talk now about composition, because composition is one of the things that functional programming is really big on, and it's one of the things that makes libraries really nice, really easy to use. So you can compose finite state machines in many different ways, and let's have a look at a few of them. Oops. Okay, so two main ways of composing finite state machines are sequential and parallel composition. In fact, we've already seen these, we've already seen sequential composition. This is an example of sequential composition. So you can think of each particular shape as being a finite state machine, and then the entire animation is a sequential composition of these three different sub-finite state machines. There's the circle finite state machine that goes through the little circle animation, then the square one, and then the star one, and we compose them sequentially to produce the entire animation. You can also compose things in parallel. Here we go, exactly the same thing, but now we've got two instances running in parallel. So you can do that. This is again, probably more use for some of you if you're doing like parallel processing. You can think of running little state machines in parallel. That might be something that's useful to you. Right. These two methods correspond to monoids. If you're familiar with the concept of monoid, I'm trying to just draw some parallels here to make them fit into your existing knowledge. There, you can think of sequential parallel composition as being the operation on a monoid. It's associative. Doesn't matter where you put the brackets, you get the same result. And there's an empty thing, which is like a finite state machine that does nothing. That's your identity element. Okay, so there are other things that we have. Should I change that slide? Maybe I need to. Transducers, where we have this notion of an output, we can also map on that output. We can apply a function to it, and we can also have flat map if we like. So that means that transducers, we can have functors and monads for so desire. So we can think of that as being going on in this animation, for example, where the what we have sort of underlying this is a little transducer, which is just counting up numbers basically, and then we map on that to produce the shapes, and they map on it again to change the colors. So it just allows us to just transform the output in a convenient way and get reusability there. All right. Yeah, I think I'm showing all versions. Okay, map and flat map, good. All right. So that's what I wanted to show for this tour of finite state machines. Let's go back over the main points again. So the main point we get from finite state machines is we get clarity of thought. When we model something explicitly as a finite state machine, it forces us to think about what are all possible combinations of state and input, and what should we be doing in each combination. So we don't get mistakes, or at least it can help us prevent mistakes. It can help us make sure we're saving all the information we need. It can help us make sure we don't get into situations where our code crashes because we haven't coded up a particular combination. And that, to my mind, is the real power of the finite state machine. Just recognizing that something we're dealing with has this form, and then thinking, okay, this is a finite state machine, so let's be really clear about what the state is, let's be really clear about what the input is, and let's make sure we consider all the combinations so that we don't put a bug into our code. We don't need to actually have a finite state machine abstraction in our code to get the benefit of this. It's really a conceptual thing. It's down to how we think about the code and then how we program it as a result, rather than explicitly modeling this concept in the code. That, I think, is the most important part. I hope I've showed that finite state machines are widely applicable. We've had different examples here. We've had the user interface, had our animations, and we talked about the web service as well. So lots of examples there. If you work in analytics, you probably have finite state machine situations, accumulations, and so on. Distributed systems, we often model them as finite state machines because it makes them easier to reason about. Things like a future, for example, is a finite state machine, has different states, maybe waiting, cancelled, failed, and so on. So lots of uses of finite state machines. Find them all over the place, very common. And the other great thing about finite state machines, why they're so nice, is that they're simple. That's one of their main benefits, really. Once you cut out the sort of terminology and the maths jargon, you get something that's very simple to implement. We sort of you can implement the core of it, just one function. And it's code that's simple to implement, generally also simple to reason about. And that gets back to this conceptual idea of, which I said, the main benefit of the finite state machine, which is forcing you to really think clearly. Am I handling everything I should be handling? Am I doing the right thing in each case? So finite state machines are really easy to reason about. And that's why they're used in theory as well, because you can prove things about them that you can't do in more complicated setups. But as practitioners, we're not normally proving stuff, so we do more informal reasoning about code that is relevant to us. Finally, there are deep connections. So if you're steeped in functional programming lore, then we've seen some of the things here, so that finite state machines are monoids, and the transition functions are called monoid actions, some semi-group actions, functors and monad instances, of course, applicative instances. So if you have this functional programming toolbox already, then finite state machines fit into that toolbox as along with all the existing concepts. So you should be able to pop them in there, going through existing knowledge and make those connections. And that, I find, is always useful, because it's nice to be able to think about things in terms of things we know already. All right. So that's what I want to say about finite state machines. Thanks for your attention. I guess we jump into spatial chat now.